How do the individual, discrete quantum states of a single atom transform into the continuous pathways that allow electricity to flow through a solid? It begins with an isolated atom. Here, electrons are restricted to discrete energy levels, the 1s, 2s, and 2p orbitals, with nothing but empty space between them. When a second atom approaches, the Pauli exclusion principle prevents their electrons from occupying the exact same state. This forces the original energy levels to split into two distinct, slightly different molecular states. In a solid, where the number of atoms is massive, this splitting occurs billions of times. The spacing between these levels becomes so small it is virtually zero, merging the discrete lines into a single continuous energy band. This result is the defining principle of the theory. In solids, atomic orbitals broaden into energy bands because of this massive periodic interaction. This transition from discrete lines to continuous bands is the physical framework that allows for everything from simple wiring to complex processors. Modeling this behavior is difficult because an electron in a crystal acts as both a localized particle and a delocalized wave across the lattice. To capture both behaviors, we rely on three distinct mathematical perspectives that converge on a single quantum reality. First is the tight binding approximation. Often called the chemist's view, it focuses on the physical overlap of individual atomic orbitals. Second is the Kronig Penney model, the physicist's view. This treats the crystal as a series of repeating energy barriers that interfere with electron waves. Finally, we use Brillouin zones. This is the mapper's view, which translates these complex wave motions into a manageable map of momentum. By synthesizing these three views, we gain the predictive power to understand exactly how any given material will conduct electricity. The tight binding view assumes electrons are localized near their parent atoms, but can hop weakly to neighbors. Think of these atoms as houses. The hopping integral, T, measures how easily an electron moves between them. Closer houses mean more overlap, making the hop easier. Hopping strength determines bandwidth. Weak overlap creates a narrow band. Strong overlap creates a wide band, allowing high mobility. This band curvature determines effective mass. A steeply curved band, a high second derivative of energy, creates a light electron that accelerates quickly. By calculating these orbital overlaps, we can determine exactly how mobile a material's electrons will be. Switching to the physicist's view, we treat the crystal as repeating potential energy wells that the electron travels through as a wave. Under Bloch's theorem, the wave function adapts to this periodic structure, becoming a plane wave shaped by the repeating lattice. As the wave moves through the crystal, it reflects off the periodic ions. At certain wavelengths, these reflected waves interfere strongly with the forward-moving waves. When the electron's momentum reaches the boundary of the first zone, these waves mix to form standing waves. These stationary waves are stuck. They cannot transport charge through the crystal. The math shows that at these specific energies, the function f of e exceeds the boundaries of positive and negative 1. In these regions, there are no allowed electron states, creating a forbidden band gap. This proves that structural periodicity acts as a physical barrier, stopping electrons at specific energy levels. While a crystal lattice is effectively infinite, its physics is periodic. We only need to map the unique wave motions within one repeating unit. We move from real space, where atoms physically sit, to reciprocal space, a map of all possible electron momenta. The first Brillouin zone is the unit cell of this map. Plotting energy to momentum here captures every unique state available to the electron. In three-dimensional crystals, these zones take on complex geometric shapes, dictated by the symmetry of the lattice, such as these simple cubic or hexagonal structures. These zones provide the roadmap to visualize and navigate the entire electronic structure of a material. When we combine these lenses, we see a complete picture. Tight binding shapes the bands, the periodic potential creates the gaps, and the Brillouin zones map the boundaries. The result is the electrical spectrum of all matter. Metals have partially filled or overlapping bands, semiconductors have small, bridgeable gaps, and insulators have large gaps that electrons cannot cross. Electrons populate these available energy states from the bottom up, similar to water filling a container. The energy level where that filling ends is the Fermi level, and its position relative to the band gaps is what ultimately dictates conductivity. By manipulating these variables, the physical spacing of atoms, or the lattice's potential energy, We can move that Fermi level and change how materials behave. This predictive power is what transformed material science from trial and error into an exact engineering discipline. In LEDs, an electron dropping across a tuned bandgap emits a specific color of light. Solar cells work in reverse, absorbing photons to push electrons across the gap. Transistors control electron flow by tuning mobility through the lattice. This model also explains graphene, where the unique hexagonal lattice forces bands to meet at specific Dirac points, allowing electrons to move as if they have no mass at all. Today, we are looking toward quantum materials, where the fundamental symmetry and shape of these bands create entirely new states of matter. This final summary defines the core of our electronic world. The periodic architecture of a crystal is exactly what forces these energy bands and gaps into existence.